So in part 2, we're going to finish off the restoration of the chassis, check the wiring, make sure that all the capacitors are good, and we have all the safety systems in the transmitter. Remember, this thing was designed in the 60s. It might not have the best system for protecting the Novice from a shock. So let's go through the radio, make sure that it's sound and ready to go, and we will try to actually fire it up, see if we can get a few watts out of it, and that'll be the part 2 of this Novice Handbook Transmitter series. So a couple of things as I go through the transmitter that I'm seeing. First of all, I did want to replace the simple lamp cord that the radio had with a proper 3-wire cord. This is just a computer cord that I've cut the end off. Most modern computer cords have the European wiring code. That is blue is neutral, green with a yellow stripe is ground, and the brown is hot. Kind of like our black is the hot in the US standard. The white is the neutral, and the green is the ground. So I've added the fuse. Now remember, the protection radio frequency choke in the output has a rating of usually between 3 and 500 milliamps. So you might wonder, well, what's putting a 1 amp fuse, a 1 amp fast blow fuse going to do? The choke is going to burn out before the fuse blows. Well, actually, the choke will not burn out at the half amp level. That's its rated current. It's probably going to pass 3, 4, 5 amps instantaneously, maybe even more when it short circuits. And it's going to take even longer for the wire to melt through, or actually fuse. So that's how it's able to blow a 1 amp or 2 amp fuse, even though it's only rated at 3 to 500 milliamps. But having a fuse is a good idea on a transmitter or a receiver. So also I have replaced the older dual cap, which was a dual 8 or 10 microfarad type capacitor, with a pair of 100 microfarad 450 volt caps. You're saying to yourself, oh my God, that's 10 times larger than the value of the capacitor that was in there. That's true, but these capacitors are low cost, and having extra capacitance just means better filtering. Now, there's so much capacitance here that you probably could dispense with the choke completely and replace it with a 125 ohm 20 watt power resistor. And with that much capacitance, I think you'd be just fine with this transmitter. So you dispense with the costly power choke, replacing it with a resistor with capacitors that are this size. This is a nice bleeder resistor that's going to take care of keeping the regulation decent. And remember, most of the regulation we're getting from the VR tube that's up here, the VR 150. I did find that the guy was short on solder lugs, and he just wraps the wires around the nuts, which worked okay, but it's funny how he went deluxe on some things but skimped because he didn't have any solder lugs. That didn't make sense to me. Also, I've been pestered that the capacitors that are in there across the line from neutral and hot to ground, typically they are ceramic discs, and these are 001 microfarad 1000 volt ceramic discs. These are absolutely fine across the line, but they are not what we call safety capacitors. What's a safety capacitor? Safety capacitors are these blue capacitors that you see inside computer power supplies today, and most appliances, microwaves and so on, will have these safety caps. Well, what's so special about them? They basically are made to be flame proof So if you have a breakdown, they don't cause a fire, and they're also rated at many times the voltage, and they handle surge voltages much, much better than the traditional ceramic caps. So we call them safety caps. They have all the approvals and all the testing and all the certifications and the stamps and the paperwork that prove that they can be put across a 120 volt or a 230 volt Euro AC line. So I thought I would add those in place of the original capacitors, just to show them off, just so you guys can see the modern type capacitors that you should be using across the line. Now I put them on the other side of the switch and on the other side of the fuse. So should anything go wrong, the fuse again will blow. So a couple of things before I move on to doing some wiring correction on the bottom of the chassis. I just noticed that the main coupling capacitor into the Pi network, the lead is broken off, so we'll replace this high voltage coupling capacitor. Very important cap. Also, the way that they put the parasitic choke and the plate cap on, I don't like this because you could accidentally touch these points, and these are high voltage, so we need to do a little bit better job on the plate cap assembly on top. Then we'll flip it over and start on that. Oh, one more comment. Notice that the meter is not bypassed to ground right at the meter. That's bad practice. Generally, some radiation can come out of the meter, and you normally have your bypass caps on each side of the meter, and that actually is shown in the article. They chose to put the bypass caps down at the other end of the leads. So I kind of disagree, and I'm not going to take those out. I'm just simply going to add a couple more at those points, just for best practices. So cleverly they put the current meter in the cathode instead of the plate circuit, which means that these terminals are at lower voltage than if they were right in the B+. Nevertheless, they probably should be bypassed right to the chassis here. So I will add some capacitors from these points to ground. I'll come up with a ground system that probably involves drilling a hole in the front panel and a flathead screw or something coming through. The connections from the front panel to the two capacitors, I noticed these washers were used to build that up. I need to take those apart and make sure I've got good connections to the panel. Otherwise, you'd have to strap these capacitors down to the chassis. Make sure there's good contact between the variable capacitors and the front chassis, because that's the only way they're actually grounded in the circuit. That's about it on the top. I'm going to clean this up a little bit and make sure I've got good connectivity between the frames of the variables and the front panel. And then we'll start the wiring on the bottom. Okay, and I've got the old military radio net going in the background here, so forgive the noise. So I've got the 6DQ6 plugged in. I've got the meter into the filament of the 5U4, and I've not put the VR tube in yet. We're going to bring this up slowly. Let's see if we can bring this up. So hopefully the tube is, yes, it is lighting. Okay. So there's your 5 volts for the 5U4, and I think you can see that the 6DQ6 is indeed lit up. Okay, now the high voltage leads 4 and 6 on the 5U4, 216 volts.
Yeah, I don't know who gets up who's next in line, but
Okay, right at the top of the meter at 760 volts AC. Meter warning me it didn't like that, but of course it is center tap, so it's half of that is what we send into the filter network. That's all I wanted to prove here. Next we'll plug in the rectifier tube. Okay, here's the real thing. All tubes are in. Let's start bringing her up. We don't need the meter anymore. This is where we see if we have any high voltage short circuits, that's for sure. Okay, I see a VR tube lighting. Can you see that the VR tube lit? Look at the monkey swing. Wow, that meter really is active. It's a sure-right meter, and one of the very low-cost meters of the 60s. This would not be my choice for a meter, but the note sounds pretty good. We've got a 3667 crystal plugged in. I've got a toroid coil on the crystal lead going to my RMS voltmeter. It's got like a 500 ohm load on it. This is a relative current in the crystal measurement up here in RMS volts. That tells me how much power I'm putting into the crystal in a relative fashion. So by adjusting the trimmer in the Colpitts oscillator, fooling with the grid resistor and so on, we'll see if we can bring this down, and then we'll try some of those HC49 crystals in the set. Dipping the meter, once it stops, you can actually see the dip, and look at the current in the crystal change as I dip this. It's no wonder we were blowing up crystals with the crystal current going all over the place off resonance. So I think this is going to be a very enlightening video. So everybody was saying, well, how much is it going to put out? How much does it put out? Remember, we were predicting that it would put out between 10 and 15 watts with 30 watts input power. Looks like we got just about 12 watts out on the meter into a dummy load. So it is working. Note is actually pretty good on this thing. Okay, here we are on 40 meters. This is 7065, and the first thing I notice right off, after the meter settles down, is this actually loads properly. Look at that. I can get 15 watts out of this easily on 40. So the loading network on 80 needed a little more capacitance in the output loading. They did add one fixed capacitor to the output in the article, but they need to add even more. I was not able to get the full loading on 80 like I am here on 40. So it's putting out 15 watts here, and on 80 I was only able to get out 12 watts. And the loading coil was totally meshed. On 80 here, I'm actually into the loading coil a little bit. So we definitely have a problem on 80 on loading. But the crystal here, and this is one of those CW crystals that was probably lapped back in the 60s, 70s. And it's youping a little bit. We're getting a little bit of... It's not as good as the note we had on 80. Of course, it could be just this crystal. I can try another one. But it's putting out more power on 40 than it is on 80, and that shouldn't be like that. So here's a 7167 crystal. Again, this is another manufactured crystal out of surplus. I found this crystal was very difficult to handle on the meter, just dipping. Without a watt meter or an SWR meter, it would have been hard for a novice to use this transmitter. You don't get really good dips on this like you do with a master oscillator power amplifier. Okay, this is a Peterson 7175 crystal. Beautiful note on this crystal. And putting out the full 15 watts on 40. So, yeah, it does very much depend on the quality of the crystal when you're using one of these one-tube simple oscillators. Also, note the crystal current on this guy. It's about half that I was getting on that other 40-meter crystal. Most of the crystals are up here with my relative meter at around 800 or 900 millivolts, and this guy's down a little bit. Now if I tune, I can maximize that, and that actually goes along with the power meter somewhat. If I dip, it's less. So when I get a really good dip, the crystal current is less. So here we have a 40-meter crystal that's actually marked for tripling, 21195, right from the factory, CW crystals. And so this is a crystal they would have expected you to use in a transmitter like this to triple up to 15 meters. So we're at 21195 kilohertz. Oh, what do we got for power? Got 6 watts out. Wow. Dip's better. I like the dip on it. But very sluggish. I would not want to use this on the air on 15 meters. Okay, here's a 7002 crystal that we are tripling up to 21, about 007. That's what it's coming out at. What are we getting? We're getting 5 watts out on 15 meters. That I would use. I could make a contact on 15 with this particular crystal. Here's the crystal current. Actually less crystal current tripling than it was on the fundamental. So here's a 40-meter crystal that we are tripling to 15 meters, and the thing's putting out a little over 5 watts. So this is the 7.002 megahertz crystal tripled to 15 meters. When tripling, the oscillator puts out 5 or 6 watts, and it seems to tune just fine on 15 as a tripler, actually with a better dip than I got on 40 with a fundamental crystal going straight through, which is interesting. On 80, it's apparent we don't quite have enough loading, but hey, the transmitter is working. It puts out about 15 watts on 40. It puts out about 12 watts on 80 because the loading's not quite right. And it does 5 or 6 watts tripling to 15. So we've definitely proven that the radio does work, even tripling to 15 meters. That's a 40-meter rock tripled to 15 meters. Not the cleanest note in the world, but it is working. And in the next video, we're going to study this transmitter in terms of crystals, crystal current, how it cracks crystals, how we might mitigate that issue. So stand by for part 3. Okay, our little transmitter works from the handbook. The oscillator transmitter kind of does what's advertised. It works on 80, 40, and 15 meters, putting out, you know, something around 12 watts with 80, but I don't think we have enough loading on 80. It puts out better than 15 watts on 40, And depending on the crystal, the note is not that great on 40, or it's very good. On 15 meters where it triples, it seems to dip better, but we only get out 5 or 6 watts. So in the next video, we're going to investigate these guys, these little HC49 crystals that were sticking inside the FT243s, and we're going to study the crystal current or crystal power and see if we can get them to work with a primitive transmitter like this.